There is a set of rules that are used to determine the lowest energy configuration for electrons, assuming Russell-Saunders coupling. So these rules are uh, not for the case of high or strong spin orbit coupling, but for um, the for the case where we have dominant terms as spin-spin and orbit-orbit interaction. So the idea is to find the lowest energy configuration and we need to have Russell-Saunders coupling. The first rule is that the electrons maximize their total spin. So we need to have maximum capital S. And the reason behind this is if you have electrons with the same spin, they're not allowed in the same orbital. So they're forced to occupy different orbitals. And when the electrons are in different orbitals, this is going to minimize Coulomb repulsion. So different orbitals and that basically implies that we're going to have minimum Coulomb repulsion. That's why it minimizes the energy. The second rule is that for a given spin arrangement, the configuration with largest capital L, the orbital quantum number, total orbital quantum number, capital L, is the lowest energy. So, given spin arrangement, we're looking for maximum capital L, and the reason behind this is when you have electrons orbiting in the same direction, they meet less often, and that also minimizes Coulomb repulsion. Okay, so orbit in the same direction and once again minimum Coulomb repulsion. The same idea. Number 3, for atoms with less than half-full shells, the lowest energy configuration is the one with lowest total J. So less than half-full shell implies that J is minimum. So we're going to have J is equal to the minimum possible value of J is capital L minus capital S. If it is more than half full shell, then J is maximum. It is L plus S. So we can see the application of these rules in some examples here. So for example, if you consider oxygen, where Z is equal to 8, it has the following electronic configuration: 1s2, 2s2, 2p4. So total 8 electrons. So we should only consider the electrons in the n equals 2 level. So those are 6 valence electrons. And the s orbital is already fully occupied. So if we consider p orbitals, for p orbitals we can say that the first thing we need to do is to maximize the spin. So we're going to place for m sub l 1, 0, minus 1, l equals 1, p orbital. We're putting these spins up, 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 and then the fourth one we have to put in the same orbital. So from Pauli exclusion principle, we have to basically reverse the direction of the spin, and we're going to put the fourth spin not in the minus one but in the plus one in order to make sure that L is maximized. So if you look at total spin quantum number m sub s, it's the sum of the individual m sub s values. So it's going to be 3 times 1/2 minus 1/2, that is 1. So that's the maximum m sub s, and s, capital S, is equal to 1. So that's also maximized. And we have m sub l, capital L, equals to 2 times 1 plus 1 times 0 plus 1 times minus 1. So this is going to be equal to 1. That is maximized. And the corresponding L value is 1, which is maximized. Okay, so L must be 1. And what is J? Half shell would correspond to 3 electrons. Now we have more than half full shell, so we have 4 electrons, 4 greater than 3, then J must be maximized, so we must have J is equal to L plus S, so J must be equal to 2. Another example, manganese 2 plus ion has the following electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d5. So we have the d orbital that is half full. So we're going to place 1, 2, 3, 4, 5 boxes. This will correspond to m sub l values minus 2, minus 1, 0, 1, and 2. So in order to maximize the spin, we're going to put all the same spin values here. So the total spin is 5 times 1/2. It is 5 over 2. Total m sub l is equal to minus 2, minus 1, 0, 1, 2. It is 0. And capital L then has to be 0 because m sub l is 0. And we have, since L is equal to 0, J is equal to S, which is 5 over 2 in this case. Another example is carbon Z is equal to 6. This has 1s2, 2s2, 2p2. Now in the p orbital we have 2 electrons, so we have to maximize the spin. At the same time, where we put them, m sub l should be maximized. So 1, 0, minus 1. So total m sub capital L will be 1 plus 0, that is 1. And the corresponding L value will be equal to 1, so that we could have 0 or 1. And the total spin is 1/2 times 2. It is 1. It is maximized. L is maximized. but J is L minus S, which is 0 because less than half full shell. Okay, so in order to find these electron configurations, we have the Aufbau principle, and Aufbau principle is the following. So starting from helium, Z is equal to 2, we have 1s2, and then going to neon, Z is equal to 10, we have the helium configuration plus 2s2, 2p6, and then for argon, Z is equal to 18, we have neon configuration 3s2, 3p6. For krypton, which has Z is equal to 36, we have argon configuration plus 4s2, 3d10, 4p6. For xenon configuration, which has Z is equal to 54, we have krypton configuration 5s2, 4d10, 5p6, and for radon configuration Z is equal to 86, we have xenon and then 6s2, 4f14, 5d10, 6p6, and then we have radon configuration 7s2, 5f14, 6d10, 7p6. That would be the next closed shell structure. And we have some special cases here, so let's talk about special cases in the electron configuration. For chromium, which is Z is equal to 24, you can see that it's in between argon and krypton, so it's going to have argon configuration. Then you have 4s1, 3d5. Copper, which has Z is equal to 29, has argon configuration 4s1, 3d10, and niobium, which is Z is equal to 41, it has krypton configuration 5s1, 4d4. For molybdenum, Z is equal to 42, we have krypton 5s1, 4d5. For ruthenium, we have Z is equal to 44, krypton configuration 5s1, 4d7. For rhodium, Z is equal to 45, we have krypton configuration 5s1, 4d8. For palladium, Z is equal to 46, we have krypton configuration 5s0, 4d10. And then for silver, Z is equal to 47, we have krypton configuration 5s1, 4d10, etc. So we have some special cases here. So let me separate these cases. Okay, so the thing to note here is that all subshells half full basically prefer a filled D. 5s and 4d energy levels are close, and we also have a half full subshells preferred, etc. So basically the energy of the placement of an electron in an orbital is influenced by the rest of the electronic environment, and when the energy levels are close, as in 4s and 3d, half-filled or filled d orbitals may be preferable. So also the same thing for 4s and 3d energy levels are close. So we have a preference for half full or full d orbitals. So this may lead to half full or full d orbitals preferred. Okay, and finally, the way we label these electron configurations depending on the total S, L, and J value, we have a spectroscopic symbol, so convention. So let's put this as a remark here. We use the following convention: L, capital L, J, 2s plus 1. So what does that mean? So if you have a many electron system spectroscopic symbol, if you have L is equal to 0, S is equal to 0, this means you have an S orbital. L is equal to 0, so this would be named S. S is equal to 0 would give you 2 times 0 plus 1, 1, and JL plus S would give you a 0 here. So this would be named S1. L equals 1, S equals 1 would give you, since L it's a p orbital, so it's p, 2s plus 1, 2 times 1 plus 1, that would give you 3. And then since we would require that J is equal to L minus S or L plus S, this could be 3p2 or 3p0, for example. So that's how we denote the L, S, and J using the spectroscopic symbols. Okay, so we talked about a set of rules known as Hund's rules in order to find the lowest energy configuration of an electronic of a many electron atom that obeys Russell-Saunders coupling. The rules are the following: maximize the total spin, maximize the total orbital angular momentum. If the valence electrons form a less than half full shell, then J has to be minimized. If it's more than half full shell, J has to be maximized. And the reasoning behind these is basically minimize the Coulomb repulsion as much as possible. We have given examples. We talked about oxygen. Oxygen has 1s2, 2s2, 2p4 configuration, 6 valence electrons, but we have a more than half full shell, so J has to be maximized. So maximizing S, we place the electrons in the 2px, 2py, 2pz orbitals, which have m sub L equals 1, 0, minus 1. All spins pointing in the same direction to maximize the total spin, and then the last one will be placed in m sub L equals to 1 in order to maximize L. So this gives J is equal to 2 as the maximum value. For manganese 2 plus, that has exactly half full shell, L is equal to 0, then J is equal to S, which is 5 times 1 half, 5 over 2. For carbon, we have less than half full shell, so J has to be minimized, but L has to be maximized and S has to be maximized, so we find that J is equal to 0. And this is the Aufbau principle you can see here. Basically we see that s and d orbitals 5s, 4d and 4s and 3d energy levels are close, so we have a preference to have half full or full d orbitals in the electron configuration. So these special cases are listed here, and we see that we can denote the total S, L, and J values. So for the system of interest, we can use this spectroscopic symboling as 2s plus 1 L J structure.